All right. Um, Good afternoon, class. I hope you had a good weekend. I had a pretty nice weekend myself. Just did some yard work and what else did I do? I laid in the backyard for like a couple hours and just kind of relaxed in the sun. Uh, hey, Steven. Um, I got a pretty easy lesson for you today. Hey, Rourke. Hey, Zach. So we're going to keep it light today. Today's hey Alex, Alex hey Ron as well. Alex, we need to talk about your response to the homework. I will be messaging you later. Hey James, hey Alex A, hey Mina, hey Alex W. So today we are going to talk about inductors. Alex W, I'm going to message you about your homework response. So we're going to talk about inductors. So what is an inductor? An inductor is basically a solenoid hooked up to a circuit. Okay. Oh, which Alex W? Alex W-A-T. I was about to say Alex W-A, but then, okay, whatever. All right, so it's a solenoid hooked up to a circuit. So basically, an inductor looks like this. Like that. And then, I don't know, maybe you hook it up to a resistor and a battery or something like that. Okay. But this thing right here, that's the inductor. Okay. So what defines the inductor? Well, one thing that defines it is, so typically this is a circle, right? So one thing that defines it is the radius of the inductor, which I'll call R. The other thing that defines it is the length of the inductor. And the other thing that defines it is the number of turns. So how many turns, how many loops does it have? If there is current flowing through the solenoid, then that current is going to create a magnetic field. Okay. So that there's a magnetic field flowing through the solenoid. Let me remind you what the magnetic field for a solenoid looks like. If this is the solenoid, then the magnetic field lines are pretty uniform and they go directly through the solenoid like this. And then once they're outside, they loop around like so. So that's kind of what the magnetic field lines of a solenoid look like. Okay. So there's actually a flux through the solenoid due to its magnetic field. Okay. So let's go ahead and calculate what is the magnetic flux through the solenoid. Now, to remind you, the formula for magnetic flux is NBA cosine of theta. All right. N is defined. Okay. N is just defined. It's a given number of turns. The area, I said it was a circular solenoid. So that area is just going to be pi r squared. Okay. B is the magnetic field of a solenoid. And I believe that I derived the magnetic field inside a solenoid for the um, I derived the magnetic field of a solenoid for the AP students, but not the IB students. So don't worry about it if you don't know how this comes about. It comes from Ampere's law, but the magnetic field inside a solenoid is mu n I over L. That's the magnetic field inside the solenoid. So if it's iron, then the mu is going to be greater than mu naught, etc. N and L are just properties of the solenoid. I is the current flowing through the solenoid. Okay. Theta is the angle between the normal to the loops and the magnetic field. So that angle is actually 0 degrees because the magnetic field is perpendicular to the loops. So the flux through the solenoid is, so I'm going to plug each of these items in. N times mu n I over L times pi r squared. Okay, now I'm going to sort of collect terms. Going to write it as pi mu r squared n squared over L times I. So why am I writing it like that? The reason I'm writing it like that with I separate is really the only thing that changes for the solenoid while it's in a circuit is the current flowing through it. Okay. So all these things in parentheses are constants. They're fixed. Once you build the solenoid, all of those things are fixed. The current is going to be changing though. Okay. So now we're going to go to Faraday's law of induction. Okay. Faraday's law of induction says that the induced EMF is equal to the rate of change of the flux. And there's a minus sign, but we're just not going to worry about the minus sign for right now. Okay. So just the derivative of the flux with respect to time. Now, and remember that the induced EMF is basically just a voltage. So I'm going to write Faraday's law of induction as simply V equals change in flux over change in time. All right. So if we look at this equation for the flux, the only thing that depends on time is the current. Okay. So the voltage across the solenoid is going to be pi times mu times r squared times n squared over L times di dt. Okay. So this constant, which I said once you construct the solenoid, it's fixed. Once you construct the inductor, all that stuff is fixed. This is called the inductance, which is denoted by capital L. So that's the inductance of the solenoid. The units of inductance are called henries, which is abbreviated by H. Typical values for the inductance are, if it's a small inductor, it could be nanohenries, all the way up to millihenries. Okay. So if we were in class, I have some millihenry inductors. that we use for experiments, but other than that, it's going to be mostly nanohenries, microhenries. Okay, so the voltage across an inductor is equal to L di dt. So that is today's main formula. The voltage across an inductor is L di dt. We could derive this straight from Faraday's law of induction. Faraday's law of induction, right, says voltage is rate of change of flux with respect to time. We could use the chain rule to write this as d flux d current times d current dt. So if we compare that with V equals L di dt, you can see that the inductance is actually equal to the rate of change of the flux with respect to the current. Okay. So that is the inductance. So let's talk a little bit about inductors. This is the circuit symbol for an inductor. An inductor is basically just a curly Q. Okay, and you would write L next to it. That's the circuit symbol. And let's say the inductor has current flowing through it. If you try to increase the amount of current that flows through the inductor, so let's say I is increasing, so this current is getting bigger, then the inductor resists the change in current. So inductors resist the change in current. Okay. The inductors resist the change in current. So if you try to increase the current, the inductor is going to fight it, and it's actually going to behave like a battery that goes in the opposite direction of the current. So the inductor, because remember, batteries, they push current out of their positive terminal. So this inductor, if you try to increase the current through the inductor going that way, it's going to say, no thank you. And it's going to act like a battery and try to push the current the opposite direction. Okay? Alternatively, what if we had a current flowing through the inductor, and what if this current was decreasing? So the inductors resist the change. So if the current is decreasing, then the inductor is going to say, whoa, keep it coming, keep the current coming. And it's going to behave like a battery that goes in the opposite direction to try to keep the current going. All right? So inductors resist changes in current. And they resist it according to this equation. All right. So we're going to learn about, tomorrow we'll learn about energy in inductors, and we'll also learn about how to combine inductors, like if you have inductors in series or in parallel in circuits. And then for the remainder of the week, we'll be talking about circuits like RL circuits and LC circuits and that kind of thing. So circuits with inductors. All right, thank you for watching. I hope this lesson was pretty simple, and I will talk to you tomorrow.